Good morning again. I have Scott Courtney here from VeriSign. He's going to tell us an awful lot about how a service that we all depend on in our jobs, how DNS has scaled through VeriSign's rather impressive infrastructure. They now handle something like 500,000 DNS queries a second in a database that is constantly changing. I don't want to give too much more on that because I think Scott's got a lot to tell us, so I'm just going to let him take off right away. Scott?
Okay, thank you, Andy. Good morning. We can make this interactive or not interactive. After 2 hours, you might be ready for interactivity. So if you have anything to say, please let me know. There's two names on here, Scott Courtney and Pat Quaid. Somebody out in the hall said, was Pat my parole officer or a federal marshal based off of my picture? He's not. He's actually from VeriSign, but he's upstairs sick right now. So I'm going to do his section and my section. The only trick with that is Pat understands his section, right? So, but we'll see how we can do on that. I'm going to talk about three things today. DNS refresher, and that'll really just be focusing on some of the pieces we run, and then we'll use Google as the example, the target. Then I'll go into an overview of the ComNet systems, and by systems I mean where they're hosted, sort of macro level, what the sites look like. And once we've done that, we get into how Atlas works. That was the part Pat was going to talk about. And by Atlas, I'm talking about the engine that drives the DNS services. Now, Atlas drives other things too at VeriSign, but Super DNS, or this ComNet service, is really the marquee application for it. Atlas is our scalability engine for lookups, and you'll see how that works, and hopefully it'll make sense to you. I have to sort of be tethered here because I've got, I'm going to be pulling up a demo at 2 points in this presentation. Okay. So how DNS works. Actually, what I wanted to do is I wanted to start a lookup right at the root DNS server. So here's what we want to do. Picture yourself at home, and you want to pull up Google search, which we've been hearing about this morning. On our device at home, our home computer, or our cell phone, or whatever, needs to translate that, of course, into a number. Now, typically, what's going to happen with a site as popular as Google is it's going to be cached already, right? And so your device will already know about it. Or if it doesn't know about it, the recursive name server that it talks to one step upstream will. We're going to pretend here it doesn't. We're going to say that you just rebooted all your equipment, including the upstream recursive name server. Starting with a well-known root server, we go right to the com server. So let me stop there for a second, too. A little bit of background here. Root servers, I'm not going to go into them too much today. There are 13 lettered root servers. Are there any root operators in the room? OK, so I can speak with impunity. I can make this up. There are 13 lettered root servers. Different people around the world run them on a voluntary effort. VeriSign runs 2 of them, the A root and the J root. And we do run we do run this infrastructure from the same sites that I'm talking about, but we run it on different hardware, and we also don't use Atlas for it. We don't really need to, right? Because if you can think of a root zone, what's really in it, the top of the DNS hierarchy, is just the top-level domains immediately behind them. So I'm talking today about com and net, but you also have a lot of other domains, right, or all the other top-level domains, .org, all the ccTLDs, as we call them, the country codes, .uk, .de, right? There's not that many domains. And so a very small memory footprint. Also, another nice thing about root is it just doesn't change that much, right? Well, you have a few updates coming in where name servers change for different countries. But you really don't have a lot of updates. Because of that, we don't need Atlas. Not much memory, not much going on. It does get a query load, a little bit of queries, nothing like ComNet. But it doesn't need Atlas. So not much talk about root today. I am starting with root, though. If you look there, can anybody read the slides in the back of the room? This isn't an eyesight test. OK. And you see where I'm doing a little dig query? I pulled that number out of the air, the 192.58.128.30, that address. What that is it's the address of JRoot. And I didn't want to put ARoot up there because it seems like everybody tests against that all the time. So I was going to try a different one. Any recursive name server out there will know this already. It'll have what's called a root hints file, right? And it'll know the 13 root addresses. I think in the last 10 years, 3 of those addresses have changed, so they don't change too often. As soon as you pull up a recursive name server, the first thing it's going to do is going to go query one of those addresses and refresh its root list, right? Okay, so we can assume that it can locate a root server by IP address, and that's that first address that I'm querying. And what I do is I say, I want to look up www.google.com. Well, remember, the root only talks to the top-level domains below it. So it's going to say, it's not even going to worry about the www part or the Google part. It's just going to say com. Do I know com? In this case, it does. It knows what the com server is. And it gives the name records for the com servers. And it turns out, just like the root, there's 13 of those. Now, I did this slide myself, and I hope you're impressed by the little circle up there. I thought it looked kind of marketing-like. What I'm getting at there is, why do we have 13? Well, the DNS response is, traditionally 512 bytes. That's the way it's been in the past, at any rate. And so that's as much as we could fit in to 512 bytes, 13. If we could have put 29 in there, we would have put 29. The sites physically have been in traditionally North America, Europe, and Asia, with a heavy preponderance, a heavy weighting in the US. Okay, we look up Google, look down there in yellow at the very bottom. I just happen to pull out of the 13 one of the sites, and that's the way the DNS will work, right? It'll start sort of random-like, and then it'll have this weighting. It will go ahead and weight responses based upon what came in quickest. But in reality, what it's doing is it's picking up one name server. So we're going to take that address at the bottom for one of the com name servers, and we're going to repeat our query in the next slide. You see the dig again? We have a different address up there. That's one of the com servers that we will be talking about today to illustrate how Atlas works. One of the com server sites, I should say. Again, we repeat the same old query, www.google.com. Do you know anything about it? Well, the com servers don't know anything about www, right? They know about the second-level domains, hierarchical DNS infrastructure or design. So what we see is the com server, in this case, says, I know of 4 Google name records, and here's all 4 of them. And I highlighted one in yellow. We're just sort of randomly picking one. Again, this normally wouldn't have to happen, but we're saying we're going from a cold boot here on your name servers. I show off to the right. I didn't explain this before, but the way we're going through things. You see the .root is where we started. Then we talked to the com server. Now we're talking to a Google name server. When we talk to a Google name server, we're no longer talking to VeriSign's name server, I'm sorry, the .com name servers that VeriSign runs. I have like a little interesting fact here. I was going to put a light bulb in front of it, but I couldn't find the light bulb icon. But that's the idea. Doesn't really relate to what I'm talking about there. VeriSign has built and operates the com infrastructure for ICANN. We have 70 million names about at any time in the com database. We actually run the net database with it, so it's closer to about 80 million. If you go in there and you look and did an alpha search on there for google.com, there's the few records that might appear in front of it, that do appear in front of it as of a couple days ago, and the few that appear below. What was interesting to me is when I did a like search on Google that I got a couple megabytes back of names that have been registered just under the com and net domains, not even talking about all the other TLDs. You guys with me so far? Okay. I know DNS is old hat, but we're almost done with it, and it's kind of necessary to go forward. Okay, so we go to Google.com's name server, and we say, okay, finally, are we there? Can you give me www? And of course, that's not the way things are going to work here. There's a little level of indirection, and the Google.com name server points us to something called l.google.com. Okay, so now we say, fine, we'll go to l.google. We're doing iterative name searches, right? We just keep going, working our way down the tree. We do this final search against the that particular Google name server, and again, our query hasn't changed. Well, actually, it did change. I'm sorry. You saw that there was maybe I'll go back here real quickly. The name changed. You can see CNAME on the top line here, so you can see that www.google.com is in fact an alias for a canonical name, www.l.google.com. Anyway, when we do this final search, we're given 4 A records. Any one of these will work. And normally in your browser, all you would have seen is the name that you started with, www.google.com, and you would have gotten a response within hopefully a second or so. In this case, if you put any of those IP addresses in there, of course, the site will appear as well. Two things I want to point out here about the lookup. And the first is the name server entry for Google.com. Remember we went through two of them? It's actually kind of an interesting design that Google has here. They have a name server with a, do you see the second field in there that says 300, right? Okay, that's actually the timeout for the record, how long that DNS record's supposed to stay in cache. And if you look at the name servers for that l.google.com, it's 86,400, which I think is about a day, 24 hours. That's in seconds. If you looked at that first level Google name server, I don't actually show it on here, but that's a 4-day timeout. What that means is if you're VeriSign and you want to see a lot of Google traffic coming across our name servers, you're not going to see it. Right? On COM, for instance, the COM name servers, there's lots of queries probably for www.google.com, but we don't see them because the timeout for the Google name server is 4 days. So all that Google traffic, all that Google lookup traffic is mostly going to Google. DNS is done. Can we proceed? Okay. Okay, now we talk about the sites. This little map actually gives an overview of the entire ComNet name registry. And what we do is start at the far left, where I have something called ComNet Domain Name Registrar. So that would be, if anybody here has ever reserved a name, and I imagine most of you have, that would be where you go in, and you type, is this name available? I want something with the word Goog in it, apparently. And they'll tell you whether it is or not. The way that happens is it's all through an application programming interface to a database that runs in VeriSign's data center. That whole gray side of things, I'm not going to really talk about much. And the reason why is it's not part of Atlas. It's a traditional commercial database infrastructure, right? OLTP, you're coming in, clustered database, replicated to an alternate site, synchronous replication, backup in terms of Oracle logs, things like that. So that's a traditional design, and I think there are many people in the room who probably understand the details of it better than I would. The stuff in yellow, though, and blue is a different matter. We're going to get to Atlas in a couple minutes. The yellow slide, the yellow portion, is all about extracting data from that database and how paranoid we try to be when we're doing that and validating it and then distributing it. I think Jeff this morning in the keynote talked about distributing data around the world. And distribution is kind of a key thing for us as well, even though on, in this case, a much smaller scale. The blue stuff out there are supposed to represent sites across the various continents. I ran out of space, so I combined the Americas. But when we talk about that, we're actually talking about co-location sites, right? Again, back on the left, the stuff we're not going to focus on, traditional data center, VeriSign owned, we have them, on each coast and things like that. The blue sites is more like, certainly you would have seen with Google several years back when you go into Equinix or another facility and they've rented out cages or something. And so that's where the DNS lookup infrastructure is. Arrows. I should mention the arrows real quick in case you can't see the direction they're going. All that means is we're pushing data out to the sites and we're pulling back statistics all the time. You'll see the statistics real time in just a few minutes. Okay, I mentioned database design. I'm not going to talk about this slide at all except for the very last button, or very last bullet, and that's isolation. This is actually pretty key for us. We can't tie the database, which is inherently an unavailable system compared to the lookup systems, with the lookup systems. So what that means is if I decide to go in and change the registry schema for .com for whatever reason, I can't have that schema change make me change what I'm doing out on the sites, right? Change the, we're going to make a copy of it. We're going to extract what's in that database, and we're going to push it around the world. And I can't go ahead and say, oh gosh, every time I make a schema change over here, I got to shut down all my sites. That would be tying the availability of what we have deployed at the edge to what we have in the data center. Entry-level DNS scalability, or what we all do. This really doesn't have anything special to do with VeriSign, right? Anybody who runs a DNS infrastructure does this or a portion of this or a lot of this. This goes for the roots. This goes for the top-level domain operators. There's several out there besides VeriSign. It also goes for people who run their own DNS infrastructure in some cases. The biggest advantage we have in DNS, and it's such an advantage compared to other applications out there, other protocols, is that DNS is client ready for failover, right? In other words, I can go ahead and I can have a resolver out there, and it'll pull back 3 name records, and one of them dies. The resolver is going to go to the next one. And the next one dies, the resolver has to go to the next one. When the third one dies, that's when the resolvers sometimes get a little bit wacky, depending on the implementation. So we have this great availability sort of built into the client, and we take full advantage of this, and everybody who hosts DNS does. Caching. Caching is terrifically important. If caching were to go away, and by caching all I'm saying is I looked up something and I'm remembering what I did, right? I looked up Google's name server and I'm remembering it for 4 days. I looked up Google's www record and I'm remembering it for 5 minutes. Caching is just taking all the queries that, or localizing your queries, right, so that they don't have to affect the whole infrastructure. If caching went away, the world would be in big trouble for name lookups. Okay, local load balancing. You know what that's about, I believe. Put many servers behind a single VIP. Global load balancing, another approach to go ahead and scale DNS. What we saw on the Google site with that, there was one name server, and then we were redirected to another name server, as it were, or referred to another name server. So what it looked like at Google, and I haven't talked to their site operators, but my guess is they have a standard DNS infrastructure at the first layer, and then they have something called global site load balancing at the next layer down. The bottom point is something I want to bring up, and that's BGP Anycast. Here, what you do, and again, I don't know if there's several network operators in the room, but with Anycast, the idea is I take an address and I operate it out of many locations, right? Many of the root servers actually run this way. We run this as well. For one of the root servers we operate, we make extensive use of BGP Anycast and run it out of 30-some locations around the world today. We do that also in ComNet for some of our stuff. We don't do it for everything, though. And the reason is, with Anycast, think about this. You have one address, right, that you're trying to go to. And if you can't get to it in Japan, you might be able to get to it in Australia, right? Because you could have an instance in Australia, one in Japan, one in the UK, whatever. And so it becomes kind of hard to debug sometimes the issues that people have. It's also, I guess it's very easy to defend downtime if you're a DNS operator, because you can always say, well, it works for me, you know, where I am. Okay, we do take advantage, like I said, BGP Anycast, local load balancing, and of course the DNS resolver. We don't take advantage of GSLB at the edge. Finally, into VeriSign's multi-site design. What is it all about? Well, our real design point is availability, right? But since this is a scalability conference, I'm going to talk about the next point down. Massive over-provisioning is what it's about on the scalability side. VeriSign's a security company, right? So we don't really, we have DNS people, we write RFCs, we have root operators, but we're really about securing ComNet in this case and the root servers that we operate and some of the managed DNS that we do as well. So we have to, in order to get massive provisioning, what we find is even though we have what looks like a trickle of queries, and a trickle to me is something, you know, like 400,000 a second, even though we have not many, we prepare for much more than that. We prepare for big attacks. We prepare for dumb things to happen. We have, and you'll see this as I get into the site, dynamic filtering capability built into the actual name servers themselves. The ComNet name servers, that'll be the Atlas sort of thing, aren't running bind, right? Or running tiny DNS or anything else. They're running our own implementation. That's one thing Atlas provides, is the name resolution. Next point down, the plan. Plan announced by our CSO this year was 100 active physical sites. And we are working with that, and we're trying to roll out sites. Now, the 100 sites aren't 100 big sites, right? A lot of them are little teeny things. Remember, we only have 13 letters. So we have to somehow do 13 letters out of 100 sites. So what you end up seeing is one of the letters being Anycast just all over the world, but in very small implementations where, you know, it'd be inside an ISP's, a single rack, for instance. When we do this idea of having many little sites, we don't necessarily advertise them on the open internet. We've run into problems before, in fact, with We had a service running in a large Asian country, and what was happening was we had 50% packet drop as we sort of left the borders, right? So we ended up just advertising it within that country and got around the packet loss. So we don't always advertise these little sites on the open internet. They might be just within your own ISP. Parallel sites preferred over complex parallelism. I'm going to get to this point again and again. I think you all probably know it. We are sort of fanatical about the simple design of Atlas and the simple design of our sites. We would much rather have a simple server that can die, fall over, that doesn't need to have 4 power supplies, even though it needs 1, and 4 cross connects on the network cables, and extra processors or whatever. We keep them really simple. As a matter of fact, the more you put into a server, sometimes the lower the availability, right? I've not seen too many boxes that can lose a processor and actually stay up, or even lose a memory stick. Last point here, major sites are rotated, swung manually during maintenance. Maintenance does happen. We don't like to show that it's happening. We don't like to affect anybody with it happening. So if we happen to know, for instance, in London, that there's some major work going on, that they're going to be playing with a router, one of the people providing us transit, we'll go ahead and we'll take the IP address that was served out of London and we'll swing it somewhere else and serve up the queries from there. Local site design. I said simplicity. Simplicity is, again, what it is about there. We hear this a lot in our shop. We try to minimize every line of code, every piece of gear, every little distance over the wire between the customer or the person using the service and the service itself. Simple concept, sometimes a little bit hard to do in practice when you try to marry different products together. Second, the service responds locally without dependency upon external systems. Huge. I told you that a database update should not require us to take down the constellation of our servers, and it doesn't. We try to make these things, it's sort of a principle of isolation, right? We try to make every box stand on its own. If I lose a box, the load gets moved over to another. If I lose a process on a box, it's detected. The box gets taken out of rotation. If I lose another box, it's tied to 10 other boxes. All 10 drop, but the others on the site pick it up. So everything's sort of modular and isolated. It's done that way at the code level. It's done that way at the systems level. It's done that way on the statistics and the monitoring that we do. Everybody's supposed to have their own little independent operations. Design layered for scalability. I sort of got to this a minute ago, and I'll get to that later. The idea of how we have, when we get into a site, how we have layers of servers, and we can take some of them down. Diversity. This sounds like a good idea, and then you try to implement it, and it becomes less good. But at least for your workload, right? The idea with diversity is we don't have a single OS sitting out there, right? Or we don't have a single hardware platform. If, for instance, we were on Intel, we wouldn't be at Intel on all our servers at that particular layer. We do this at the router layer. Router's a little tricky. I get the load balancers, of course, with the servers, and with the code as well. We have our Atlas code, but we have other code, diverse code sitting right next to it, and it's live. It's just not getting traffic. So if Atlas were to die this afternoon, then this afternoon we would be running on a different set of name server code. Routers. The reason I mention that is we get to layers, right? I talked about that picture of me when I got started, and I think I have probably a 30% chance of having a good picture taken of me, right? That's what they mean by not photogenic. It means really you're not attractive, so you have to get in there and catch them at the right picture. And then I think at VeriSign, when I had that picture taken, they had like a 30% success rate of making me look good, right, with the camera and everything in the situation. So if you look at the availability between those layers, or you look at the probabilities, we say 30% of this, 30% of that. My over probability of looking good is about 9%, and that's why the picture was so bad. Right here with routers, we have the same sort of situation. If I have or between any of these layers, if I have a router layer, for instance, it's a Cisco layer, and I have an ISP router, the ISP is running something like Juniper on top of that, right? And I have a day zero exploit, and it takes out every Juniper router on the network. And I say, well, thank God I'm running Cisco. Well, that's true, except I get no traffic to my site because the upstream router, which is in series with it, has now failed. Monitored boxes are independently monitored. I will show you that. No one administrative plane is used for the systems. I think this is old hat to everybody here. Automation. This is, we're going to put a picture up right after the slide. Automation. We have automated zone updates occurring all during the day, right? So if you go and you decide, I really want, I'm a Mickey Mouse fan and I'm not worried about Disney suing me and I want to reserve Mickey Mouse is my favorite character.com, you can be gratified to see that sometimes within, depending on how fast the transaction was submitted into the database, within 15 to 30 seconds, you can usually see that running around the world at each one of the sites. Those updates are constantly being extracted, validated. This whole process is running and pushed out to the edge. It should be on what we try for is a 15-second cycle, an update every 15 seconds. That's all automatically applied. Load is transferred if servers fail. That's standard load balancing with use of a health check. And then last point, all components active. Huge point with me. I don't know if you've seen, sometimes it's better to talk about failure, right, than the way things work. And this didn't happen on Atlas, but it's happened in our other infrastructure before where we had a active load balancer and a passive load balancer. And with the passive load balancer, somebody pulled down the internal facing interface, right? But that's not really monitored and you don't have live traffic going through it. So what we do is we took a hit on the active load balancer, a hardware hit, it failed, flipped over to passive, which is now active, and it was working great on the top. It's just kind of reached the ether behind that. And so the site was unavailable. What we prefer is all active equipment. I don't want spare sitting in racks. I don't want spare sites if I can help it. Active to everything. Nothing like production traffic to flush out an issue. I didn't want to go there, so let me show you a picture now. This is monitoring for ComNet. We do other things with, we do other monitoring as well. There's little teeny tabs at the top for some other things that are there. You're actually looking at a development system right now. The feeds on it are production feeds. So this is the activity being seen right now, ComNet across the world. On the left-hand side, there's a little speedometer. It says 265,000 queries a second. It's a Saturday. Saturdays are usually about 75% of the traffic of a normal day. The peak that you see in the, you see the little graph here with the red traffic jumping around, that's today. The green line that it's following is last week. Green line, of course, is averaged, so that's why it looks smoother. You will see this almost every day outside of an attack sort of situation or a misconfiguration problem on somebody's name servers. You'll see this very smooth pattern in the sense that it'll follow last week's pattern, right? Sometimes seasonal changes will happen where you get a little tick up or a tick down, but almost always you'll ride on top of the last week. You also see that this is Eastern time. I apologize, we're mostly Eastern operators at this point. You see around noon Eastern time, 11 a.m., 1 a.m. Eastern time is the busy time for DNS for whatever reason. That happens every day of the week. Okay, the little green dots are sites around the world. We have some statistics at the top which are somewhat believable and not really. It is hard to believe that Peru is generating 10% of the traffic across the world, so I think that might be South America, right, altogether, and maybe Central. You can see top requests. People are requesting these names that are showing up, and hopefully nothing nasty will show up while we're here. This is where you won't ever see www.google.com, or you shouldn't, right? Because again, Google's got that 4-day timeout, so we just don't see their name traffic. The ones we see here are sites that might be a little site that all of a sudden got a / dot effect, or maybe a little site that's under attack, or possibly a site that's got a misconfigured name server, site that, anyway, problems like that or issues like that are why they show up. On the far right, we've just broken down what you're seeing over there with all the little dots in case you can't read the dots. So on the far right, we've got our various data center or co-location sites that we're running things out of. And you see the TX column, which you won't be able to read, but that's transmissions. We have something called send file. TX means just the number of queries that are being received at the site. I'm sorry. Send file, the SF, ISF, all those are talking about are updates. Remember I talked about updates going out every 15 seconds? Well, we're tracking here how far we're falling behind. Palo Alto, for instance, is 6 of those 15-second updates behind. if it becomes a large number, we will take the site out of rotation. It'll generate alerts. I'm going to get back to monitoring in a little bit, but this is where I transfer over to the Atlas side of the conversation. And could I have a time check in the back? OK, very good. So we're now going to talk about the Atlas design and that we use for SDNS. Yes?
Regarding request redirection, during regular cases, I assume every DNS request goes to the closest in terms of latency. Whereas, what do you do in terms of like DDoS attacks or anything? You just spread the load, or you have other filtering mechanisms? Talk about that.
Yeah, I'll try to. The question was, what do we do in the case of DDoS attacks? How do we filter them? How do we redirect the traffic away, say, from a particular site? Maybe I'll get to that, and if I don't, consider that I skirted the question because I don't want to answer it. But I'll try to get to it.
What kind of traffic growth are you seeing?
That's a good question. What kind of traffic growth are we seeing in the requests per second? When I started at VeriSign, which is 3 years ago, the peak was sitting closer to around the 200,000 or something like that. So it's gone up sizably, but the traffic growth is actually much smaller than what we'd have for something like text messaging. I don't know if you follow that, where it seems to double every 3 months in this nation. Still, we're seeing traffic go up. It's kind of interesting. You see on the internet, spam never goes away, viruses never go away, right? And so I guess we should expect that this will continue. Should I get into, you ready to go into Atlas? The Pat Quaid portion of the lecture or talk? OK, introducing Atlas. Key challenge, keeping up with 4 million updates a day. The 4 million updates we're talking about here are the updates coming into that OLTP database. Now, it may seem strange to a lot of you that we would be getting 4 million updates a day into the OLTP database. Names are, we all want names, but why would you grab 4 million of them? In fact, what we're seeing is maybe 1.5 million adds, 1.5 million deletes, and something under 1 million mods. Anyway, it sort of works out to about 4 million. Why would you have so many deletes and so many adds? That gets into the phenomenon of domain tasting that the world has seen over the past few years, where people will acquire names, hold on to them for up to 5 days, and then get rid of them if they're not generating ad revenue or something like that. Serving more than 20 billion requests a day. When I read that, I always think of the old McDonald's thing, right? 20 billion burgers sold or whatever. We're mostly concerned with requests per second, not how many we get per day. VeriSign's answer is Atlas. Atlas was begun a development effort back in 2000. It wasn't until 2004 that we actually turned it on and put the other system on standby sitting next to it that had been there before. So really careful with ComNet. We haven't had an outage. Knock on wood, we've always been available. We're expected to be always available. That's what our SLA is. It is 100% with ICANN. And that's another reason why we have so much redundancy built into this and so much paranoia. Atlas provides, bottom bullet, a framework to manage DNS resolution services, and then infrastructure for the other services. Some of the other services are OCSP, if you've heard about that. That's for certificate revocation list, the new way of doing it, so you don't have to pull down the whole list. Whois, if anybody here uses Whois for COM, we run that Atlas on that. Our managed DNS is another one that we run on it. We do a VoIP lookup service. So it is reaching into other areas of the company. Nobody sees the traffic in the company that SDNS does, though, that ComNet does. Let me go back to presentation view here. Where's the little dot? I don't normally do PowerPoint. My apologies. OK. When I drew, here's what you have to remember. You know what? I'm going to just show you the picture again. Let me flip back real quick. Entry level, database design. There we go, way back there. When we drew this up, remember we have the yellow systems that get the data out of the database and are paranoid about that, and then we have the blue systems to serve them up. We're going to talk about the yellow systems right now, the systems that get the data out of the database. Atlas, distributing updates. OK, very good. So I'll go through here, try to be quick. I've got a lot of talking to slides, so I'm going to hold the slides up, and you can review them on YouTube if I don't cover the individual points too much. Data integrity cannot be compromised. We can't have, these sort of things have happened in the past, right? But we can't have, for instance, Microsoft.com pointing to another site. That would be very bad for, let's say, your security updates you pull through it. It'd also probably be bad for the poor little site that got just overwhelmed with the traffic. That'd be an attack on its own. So we have to be very concerned about data integrity. Updates, when we do updates from the database, we got to distribute them so that they actually appear at our sites without gaps between names, right? We would hate to send some updates and get them out of order, or drop a few and just say, whoops, we missed. Sorry about that. Scaling issues, I've talked about there. The one that's kind of interesting is just keeping up with the number of sites. As we go to 100 sites, distributing the updates starts to take more and more processor resource, from our first hub that we distribute to. In terms of distribution, by the way, we use a hub and spoke approach. We pull from the database, do our things there, and then we go out to a site. Then once we're at a site, we distribute to some of the boxes at the site. The first little yellow box at the bottom was extraction. How do we extract data from the database? We try, again, to keep the simplicity rule here. We have, I'm going to just, let's see, jump down to the middle selection. We collect updates into files. So you have this Oracle database. The updates are coming into it in a certain order. We're pulling them out of it in a certain order. Again, we don't want to get the order wrong, right? We don't want to. A lot of people, what they'll do is they'll delete a name server and add a name server, which is good. It would be bad to add a name server and then delete it, right? And then they'd have no name server out there. So we're very careful to serially order the updates into. And what we do is we pull them out of the database and we just put them into little files. Now these little files that we put them into are those send files, or those things I was saying get shipped out every 15 seconds. So you pull a bunch out of the database, crunch on them for 15 seconds, and distribute them out. And then you pull the next bunch out while they're being distributed, and so on. Actually, yeah, OK. And that's the way it works. We pull them out and distribute. So those are called those are the 15-second updates. The very bottom thing, periodically dump the database, that gets into the restartability thing. We want to be able to restart our name servers that are running in the constellation periodically, and by periodically, maybe twice a day. And that's sort of a key design point with us. Any server, any service needs to be able to be restarted. So what we do here is we pull the whole thing out. We pull the whole thing out, and we ship it out to the edge sites, and we reload the databases. We don't do it all at the same time. If we were running bind and we did a reload of ComNet, it would take over 20 minutes, I believe. It takes us less, but it still takes a bit of time. So we have to sort of stagger our updates. It's really interesting. Those of you who've run DNS, if you've ever worked with an 80 million record zone file, it's just a little different business, right? You don't grep it, for instance. That's a few minutes to pull a record out. Validation. Terrifically important here. We extract. We distribute. I'm going to get to distribute just on the next slide. But while that's happening, in the background, we're validating each name that we pull out of the database. Each and every name gets verified, right? So we'll pull them out, and then we'll go back in and check the database. Did it look good or not? We also take that stuff, and we pull it into the validator box. Looks an awful lot like the boxes we have running as name servers in the constellation. So the same server, same operating system, same in-memory image. And the reason for that is by pulling it into the validator and checking on something that resembles what we have in production, if the validator were to fall over, we might say, hey, that might not be a good idea to push that out and knock everything over. Sometimes validation, of course, can be a little tricky because we have all those domain name updates coming in. We're 15 seconds behind, so we have to play a few games to keep in touch, to be able to flip back and guarantee that what we're seeing in our validator actually was what was in the database 15 seconds ago. If we do see conflicts at this point, they're bugs. They're bugs in the system. I'll give you an example of a bug. Somebody goes ahead and they request a domain. They create a new domain name, and for some reason we haven't correctly coded for that, and so we push it over the validator, and it just sort of splats, right? It doesn't know how to handle it. That would throw a red alert, exception, and we'd all go clamoring to fix that right away. The last point I want to mention is we do have the concept of marquee domains, VIP domains. That would be a domain that gets a lot of traffic, and it would be a very bad thing for us to send traffic elsewhere. So we, in those cases, if you, at any rate, we keep a little VIP list of domains that get a lot of traffic. I see some people in this room who are at companies that would be good candidates for that list. Distribution, this is just that concept of we extracted, we validated, let's get this thing out to the edge. This actually happens while validation is going on. So we push these things out to the edge because we don't want to wait, and then we'll send a little teeny control file that says, yeah, go ahead and apply it. The idea here is, I didn't know if you noticed some of the sites we have. We have one in Kenya. And Kenya's a challenge because it doesn't have a lot of bandwidth, and every time it rains, the site goes offline, it seems like. So we have trouble sometimes getting updates out there, and we can't use the normal TCP approach, right? Because when we do that, we would be seeing our window restart because TCP doesn't do well with even 0.1% packet loss, but you pull it to like 20% packet loss, it becomes a real bear. So we have this very brutal UDP way of pushing files out. Double check every step of the way. I think I've talked about validation. We use checksums on every packet, and we use checksums at the full file. And then last point gets back to isolation. No global synchronization. Remember we were looking at that slide, and I showed you Palo Alto with 6 SFs behind, but some sites weren't. Some sites were current or 1 or 2 behind. We ship them out, and it's almost best effort, right? The site gets it, the site gets behind. If we see the site get behind too far again, we'll take it out of rotation. But we don't try to put complex software in place to ensure that it all gets out there at the same time. And this big lockstep across all the sites we have that we're all ready to jump, let's apply the change. We don't do that. We covered the yellow stuff. Now we're going to the blue stuff. The blue stuff was actually the sites themselves. What do the sites look like? Okay, and I'll show you that in just a little bit. Okay, we talked about the traffic to the sites. DNS is susceptible to spikes. These are really interesting. It does seem when something breaks, it is much more interesting than hearing how it works. You actually usually get the true story too when it breaks. We are susceptible to spikes. DNS is susceptible to spikes. That's actually as bad as an attack on us. So what we try to do is we try to educate the community in some cases, and we just try to add lots and lots of servers and services to get around it. There's a paper out there written by a couple guys that I work with, Matt Larson and Pete Barber, that it's an RFC that was published last fall that goes into some of the things that happen. It does bring to mind the old cliche, never attribute to malice what can be explained by incompetence. You would be surprised at what some of these name servers have done, right? You'll Okay, go on. Twin goals, minimize response to bogus traffic, and of course, maximize response to valid traffic. At the DNS site, we have a front-facing box. This box, all it serves to do is get interrupted. I don't know if you're like me, but if I'm at home and I'm working on something, I really don't like the doorbell, if I'm in the middle of something, or the phone ringing every 5 minutes. The PE, on the other hand, or this box we're talking about, is just designed for that, right? It doesn't have a big brain. It doesn't have much memory, and so it does well getting interrupted. Not that you're supposed to read into that. So what we do here is we have all the queries that we're receiving coming in on these little front-end boxes. And they look a lot like the boxes Jeff described this morning. Commodity, cheap, not a lot of availability. If they roll over and die, they die. We'll get to them in 30 days. We'll get to them in 60 days. It doesn't matter. We have the redundancy at the site. We have redundancy across the sites. Balance sets of front-end, back-end machine, logical name servers. I'll get to that in a second on the next slide. To the extent possible, traffic pattern monitoring is out of band. And what that's talking about is we actually do monitor for attacks and things. We try not to do that on the PE too much. The PE, or this box that I'm calling PE, does fulfill 2 important roles though. One is it pulls the queries in, bundles them up, and ships them out to a big name server. Then it gets them back and it sends them back out. Okay? The other thing that's really important with it is this is where we can do filtering. This is some of our DDoS defense that you had asked about. We can push filters out to the PE and say, you know what, ignore queries that look like this, that are from this address. The second server, and this is, there's really only two that are involved in name lookup. We have the little one that gets interrupted, and he bundles queries, and he sends bundled queries onto this other server sitting in the back of him. That's the traditional big name server. Again, running Atlas code. In-memory database. And why am I in frontline server? OK. And so what you see is that front-end server that gets interrupted since its query's down here. A lookup happens here. The lookup after, what we do is we bundle a couple of responses together, and we ship them right back out to the front-end server. OK? This box can handle many more queries than one of those front-end boxes. Usually, right now, today, we have about a 10-to-1 ratio. 10 little front-end boxes to one of these. These boxes have a lot more cores, a lot more RAM. Go on. OK, I'm done actually talking about the infrastructure. And I just am going to put this slide up, not talk to it too much. I'll let people who want to look at our ways of coding, they can refer to the slide in here or ask questions about it. We also do a lot of testing. I only want to make a couple points on this test slide. We test to the breaking point. When we do test to the breaking point, what we do is we have a test environment that looks just like one of those production sites you saw, and then we'll throw whatever the query limit it is that the site can handle against it. And we're really interested in layer by layer interaction and then interaction across the layers. One thing that we learned is that monitoring system that I showed you a few minutes ago is the one that we also try to use now in test. What we were finding is the people in test, including my own team, were writing scripts. And then we get out in production and be like, oh, something weird's happening, and why aren't our scripts out there? Well, we have a monitoring system. Why don't we use it there? And so that's kind of a best practice. There's some other best practices on here that I'd recommend you look at and compare with your own notes. Seeing if there's anything I wanted to mention. Low severity, reset to known state. I've talked about that. Restartability, how important that is. Again, we get into isolation. Monitoring, I'm going to just pull up that HUD one more time, and we'll be done with that there. OK, so here we are. We're looking at different sites around the world. The top site today on Saturday happens to be Amsterdam. If I move over to Amsterdam, if I can find it on the map here, and click on it, and hopefully I'll get a response here. The trouble with doing a live demo and a presentation. I see what is at the site this in our heads-up display. So, and you'll just have to follow the mouse here. I'm going to talk to the monitor. I apologize, but I don't have a better way of doing it. So we have monitoring boxes. We have those head-end boxes. Remember I described them that I was calling PEs? Here's a bunch of PEs, the ones that get interrupted all the time. And then we have those servers, the back-end servers, the in-memory databases, and there's a number of them at the site as well. I talked about distribution and how distribution starts centrally and it gets pushed out, and we have that hub and spoke. You can see we have distribution happening and distribution servers here. If I click on any of these little buttons for any of the servers, just like probably a heads-up display you all might have, we see server statistics popping up, including resource utilization or whatever. There's a separate alerting infrastructure, but what we found is when we're under attack, for instance, it's really nice to be able to go in and see how the individual servers are behaving. So even though we might be alerting for CPU spike, it's just kind of nice to watch it go 25 or 30%. If I did click on these boxes, you won't see any CPU utilization. The COM infrastructure is idling under normal load. On that main screen where we showed the graph of activity, if you did see a DDoS attack or you saw a big spam attack, you might see it jump up a teeny bit, 50,000 queries a second or something, right? And that's a big attack for some people. If you see a real attack on the COM infrastructure, and I've seen those as well, it'll vertical bar. It'll go up and the scale will start changing. You'll hit the million or whatever queries a second. I think that the largest we saw, and it was there was a paper written about the whole attack pattern, was 5 or 7, maybe 5 to 7 gigabits of traffic, which turns into just a few million queries a second. Those weren't even queries. That was responses they were sending to us, which gets back to that earlier question. How do we handle things? We can handle it at the network layer. I'll give you one example. Let's say somebody's sending us a DDoS attack, and they say, oh, we're going to hit you with 5 million queries, responses a second. Well, that's just bandwidth to us. We don't deal with DNS responses, right? We're giving the responses. We deal with queries. So we can stop that at the routing layer and just say, we're not interested in that sort of traffic. Okay, any questions? We've got like 5 minutes, so I was trying to go fast at the end there. Anything you wanted to know about VeriSign's DNS? No?
Actually, I have a question about attacks. How long do typical attacks last?
The big attacks, first of all, there's not many big attacks, fortunately, against the DNS infrastructure. I don't think it's a wise thing to do. It puts a lot of eyes on you when you do things like that. But the one I talked about didn't last long at all. There was, I think there's attack the week before for maybe half an hour or an hour, and then the larger one was only 20 minutes. When we see DDoS against people in the internet community, of course, even like offshore gambling or some of the payment services, those can go on for weeks, right? It's more of an extortion attempt there. Yes?
You mentioned a lock-free database structure for the lookups in one of the slides.
Right.
But you didn't go over it. I was wondering like what kind of data structure you use for doing the queries themselves.
Right, okay, and the question was lock-free data structure. How do we do that? How do we avoid doing locks? I'm going to answer this as from what I've seen, right? I haven't written the code for that. That would have been Pat. But first of all, we have something very simple. All we're really concerned about are our domain names and name servers. So when we pull the data out of the database, we key it for domain names and name servers. When we have the updates going in on the site, right, there's a little 15-second update things that come in. Well, actually, let me back up. When we restart the database, when we pull the entire data structure over, we can shut the whole thing down. So we're not taking queries at that point, so locks don't apply. But when we have these little incremental updates that come in, we tack them on, as it were, to the very end of the data structure there. And we don't use a lock, but we do use, and we don't use a system call lock, but we do use I guess you'd call it a logical lock, in the sense that we'll wait. If somebody's requesting that domain, we'll spin a little on that. Does that answer it?
Yeah.
Okay. Is that it? Well, thank you for being here. I think it's time for lunch, right? I turn it back over to you, Andy.
Oh, yeah, thank you, Scott.